So the quantum mechanical model helps explain the chemical behavior of the elements. Remember we said that those valence electrons are what affect bonding for the atoms. And we see from the periodic table that the element properties vary in periodic fashion. That's how Mendeleev put the periodic table together in the first place, and why it's called a periodic table. But it varies that way because the number of valence electrons is periodic. As we go across the periodic table, we have one valence electron in the first column, and 2, and 3, and 4. And so that varies. And so we can explain what we first asked questions about at the very beginning of this chapter, the reactivity of hydrogen and the inertness of helium. So let's look at this. Let's look at helium. Helium is over in group 8A with the noble gases. Helium is an exception here because it only has 2 electrons, so it can't have 8 valence electrons. But still, it's in a level where the highest occupied shell is full. That first energy level only has 1 orbital. It can only hold 2 electrons, and it's full. So that is a good condition for it. The rest of these all have 8 valence electrons. The highest occupied level is full. The noble gases, as a result, are chemically stable. They don't react very much because this is an especially stable situation. What we find is that elements that have electron configurations that are close to the noble gases are the most reactive because they can get to a noble gas configuration by gaining or losing a small number of electrons. So here's another analogy from chemistry land. So in chemistry land, these are the cool kids from high school, the ones that everyone wanted to be like. And electrons are like the clothing that you wear and how you style your hair and stuff. And you can change that. You can't change the number of protons. You can't change who you are, but you can change what you look like. And so, high school kids, they'll change what they can, and they want to look like the cool kids. So cool for atoms is defined as having 8 valence electrons, with a little exception of helium. So if we look over here at the alkali metals have 1 valence electron. They are very, very reactive because what happens if they lose the 1 valence electron? They become like a noble gas. Let's do an example. Let's look at sodium. What color? Let's go white. So for sodium, the electron configuration of sodium is neon plus 3s1, right? Sodium has 1 valence electron. If it lost 1 electron, its electron configuration would be the same as neon, right? If it takes off 1 electron, it looks just like neon. Well, when it loses 1 electron, it becomes a sodium plus 1 ion. So sodium will do that. It will get rid of 1 electron so that it can have that very stable electron configuration of 8 valence electrons. And all the other alkali metals do that as well. They all have 1 valence electron. If they lose 1 electron, they have the electron configuration of a noble gas. If we look at the other end, I'm sorry, we're not going quite that far yet. We're just going to go over one more. So beryllium, magnesium, these guys, the alkaline earth metals, group 2A, they all have 2 valence electrons. Let's look at strontium. What's the noble gas configuration shorthand for strontium? It'd be krypton with 5s2, right? So if we got rid of those 2 electrons, then it has the same noble gas, same configuration as the noble gas, but now it's got a 2+ charge. All of these elements form 2 plus ions. Because when they do that, they then, on the outside, look like a noble gas. So, we can say they're dressing for success, or they're dressing to look like a noble gas. Now, obviously, that's not what they're doing. But it is all about energy. And 8 valence electrons is especially stable. And so if they lose electrons until they have 8, then it's more stable. And so that's a desirable thing. Now let's go across and look at the halogens. The halogens are one column to the left of the noble gases. They have 7 valence electrons. So here's fluorine with 7 valence electrons, thinking if I could just get one more electron, if I could just one more, then I'd have the electron configuration of neon. So all of these guys are in that same boat. Didn't mean to do that. All of these are in the same boat. They need one more. So they form, they form 1 minus ions by gaining 1 electron. Bless you. Because when fluorine gains an electron, it becomes 2s2, 2p6, which is the same electron configuration as neon. You see how that works? So, the quantum mechanical model of the atom explains why these elements form the ions that they do. These form -1 so that they can have the noble gas electron configuration. The next column over, oxygen, sulfur, tellurium, they form -2 ions because they have to gain 2 electrons to get that same electron configuration. And nitrogen needs to gain 3. I don't know why they leave phosphorus out, but he does that as well. The guys over here on the left, these will lose 1 electron, and in group 2 they lose 2 electrons. So these are the elements that form predictable ions. Oh, and then there's here 3. Forgot about him. So aluminum will lose 3 electrons. Because for aluminum, losing 3 this way, and then it would wrap around, he's going to end up here. Losing 3 is easier than gaining 1, 2, 3, 4, 5. So it's basically the shortest path to a noble gas electron configuration.